I'd like to begin today by acknowledging with respect the Lake Wangung speaking people on whose traditional territory the university stands, and the Songhees and Wiskwaimalt and Waisanuch peoples whose historical relationships with the land continue to this day. So welcome everyone. I'm Sybil Seitsinger, the Executive Director of the Pacific Institute for Climate Solutions here on campus. And I want to note that this seminar, as always, is being webcast. And so we also have people who are joining online. And afterwards, when we have time for questions, we'll be asking you to speak into the microphone, not so that it amplifies it within the room, but that so that people on the webcast can hear your question as well. So with that, I'd like to welcome Marcus Summerfield today, who's our speaker, and he's a PhD candidate in mechanical engineering here at the university, and he's a research fellow for us at the Pacific Institute for Climate Solutions, one of the fellows. He graduated in 2015 from the Technical University of Kaiserslautern.
Close enough.
Close enough, in Germany, and obtained a diploma degree in mechanical engineering and energy technology there. He joined the Institute for Integrated Energy Systems Analysis, ISVIC, here at UVic in September in 2015, and he's now working on his PhD in renewable energy, and very exciting, I'm sure, talk today on airborne wind energy. So thank you, Marcus, for joining us today, and I look forward to hearing your presentation. Thank you.
Thank you. Thank you for the introduction. So, yeah, with this great introduction, I don't even need to introduce myself anymore. So I'm going to get right into it. Today I'm going to talk about airborne wind energy systems, and I divided up my talk into 6 general categories. So first I'm going to start by talking about wind in general, where it comes from, a little bit of the history and the current state of the technology. Then I'm going to talk about the outlook and the potential of airborne wind energy, as well as the markets. Afterwards, I'm going to mention some challenges because this technology is still quite new, and there are a lot of challenges that need to be tackled, and that some of them I'm working on. And I'm going to talk about my research afterwards and summarize everything, and then we'll open it up for questions, I think. So first of all, does everybody understand me in the room? Do I need to speak up? Even in the back? Great. OK. Yeah, so let's talk a bit about the background. Wind energy has been used by humanity for quite a long time. Here on the left-hand side, you can see of the very early wind energy devices, or a wind turbine. This is actually like a Persian design. It's about 2,500 years old. And what that does is it's basically utilizing the drag force. So as the wind blows against these boards, it rotates around, and thereby this motion was used to mill grains and create and use for flour making. In the center, you can see wind turbine design, often referred to as the Dutch design. It's about a few hundred years old, and it was used also to mill grains or to pump water. And on the right-hand side, you can see a modern vertical axis wind turbine. And what all these designs have in common is that they are fairly close to the surface. And fairly close to the surface means we don't have a lot of energy potential, which is why most modern wind turbines look like this. So after a long time of development, the technology has converged to this standard design. We have a monopile tower and usually a 3-bladed wind turbine. And this, what you can see here, is actually the tallest wind turbine to date. It has a hub height of 150 meters, and the hub being here in the center, the nacelle. And from tip, which is up here, the tip of the wind turbine blade all the way to the ground is about 250 meters. And one of the reasons why we go high up in altitude, and I hope this is going to work, is because winds, on average, in general, are stronger in higher altitudes. Now, what you can see here is the wind situation today, and we can also see the forecast. And currently at surface altitude. Now, blue meaning slow wind speeds, red meaning high wind speeds. Now, as we increase the altitude, one second. Where's my mouse? That's the zoom. Okay, that doesn't work as expected. There it is. Sorry for that. Just wanted to show you that as we increase in altitude, even in areas where we had low wind speeds before, the wind energy potential and the wind speed on average increases quite significantly. So, and this leads to the trend which we've seen in the last couple of decades from early designs in very low parts of the altitude of the atmosphere to modern designs and new future designs that are going to come out that tap into higher altitudes. And in general, what you can see here, for one, is that the towers are getting taller and taller and taller, but also the swept area is increased by larger and larger wind turbine blades. Now, the reason why we increase the swept area is because the harvested electricity, the harvested energy, is proportional to the wind speed, for one, but also to the swept area. Now, that comes with a couple of challenges. For one, transportation is getting really, really hard at some point. We might have a great spot for wind energy harvesting, but at the same point, it's unreachable with conventional means of transportation. Another things are that the loads on the wind turbine blade as well as the tower are getting quite significant, as well as transportation offshore, grid connection offshore, maintenance offshore is whole nother problem at this point. So why not? Oh yeah, so another thing is the turbine costs. Here you can see a cost breakdown structure for a conventional onshore wind turbine. In yellow, gray, and in orange, you can see non-wind turbine related costs, such as grid connection, foundation, and planning and miscellaneous costs. And in blue, you can see everything that's related with the wind turbine. And the majority of the cost, as you can see here, is actually coming from the tower and the rotor, the turbine blades. And there were some people who had the idea, well, what could we do about this? How could we reduce the costs? Well, we could reduce it by just taking away the tower. Well, a design without a tower could look something like this, which is usually a buoyant air system, airborne wind energy system. Here you can see two designs, one being here on the left-hand side. You can see a lighter-than-air blimp filled with a lighter-than-air gas, and it creates energy by rotating around its own axis. And on the right-hand side, you can see another design, which is basically like a balloon, like a hollow balloon with a wind turbine inside. Well, what if we went one step further and removed the blade? Now, one reason to remove the blade is actually that the majority of the energy is actually on the blade is actually created by the most outer part of the wind turbine blade because of the relative velocity is highest on the outside, whereas the inside of the turbine blade is mostly for structural support and to carry the loads. So what would a design look like if we get rid of the tower and the turbine blades? Well, it could be something like this, a tethered glider. And here you can see three different systems that I wanted to highlight briefly. On the left and the top, you can see a company called Kite. And they use a kite, which is a flexible structure. Here on the bottom left, you can see a rendering from Tech. It's a Swiss company, actually got funded or co-funded by a Canadian from Vancouver. And on the right-hand side, you can see probably the biggest player in the market, Makani, and they use a rigid wing aircraft with 3 propellers. And the way it's positioned here right now, this is the takeoff and landing position. So it takes off like a drone and lands like a drone as well. I'm going to talk about this a little bit more in detail, but for visualization purposes, I've brought a little video. And here you can see Tech's smaller prototype as it takes off in the Swiss Alps. It uses propellers to reach production altitude, and then at that point it switches into production mode, the propellers are switched off, and it produces energy through pulling a tether from a winch, which you can see in a little animation in a few seconds. So as I've said, the general concept functions like this. It uses the propellers to reach operation altitude, usually a few hundred meters. That's more like 200-300 meters. That's what they're aiming at. As soon as it reaches this altitude, it switches into production phase and creates energy by pulling a tether from a winch. And the winch is connected to a generator. And if the wind gets too weak or the weather changes, it automatically lands again. So what you've seen so far are a bunch of different concepts and a bunch of different designs, and I'm going to categorize them a little bit here. In general, we differentiate two different generation types. So we have airborne wind energy systems here, and we differentiate the ground generator and the fly generator, the flying generator. And these are then differentiated further. First, we have the fixed wing ground station. Fixed ground station. As you can see, we have a fixed ground station, as we've previously seen in the video. It functions by pulling a tether from a winch, thereby generating electricity. As soon as it's reached maximum tether length, this whole system, the whole aircraft, has to dive down again, at which point the winch is then reeled in, and then it reaches its initial position again and starts the production phase again. So this is also referred to as a pumping cycle, a pumping motion, because the motion of the aircraft is going up and down. And another design that makes use of the ground generator is the moving ground station. Electricity is not generated by pulling a tether of a winch, but more by the motion of the ground station itself, usually on rails or a carousel. And we differentiate a circular motion and a linear motion. In contrast to the previous design, the tether length here stays constant. So we don't have this pumping motion, more like a continuous generation. And when it comes to the flying generators, we have the crosswind designs, which you can see here in the top two pictograms. The left one being the Makani design, a fixed wing aircraft with propellers that flies up in the air, and these propellers switch into generator mode as soon as it reaches generating altitude. And through the motion of the aircraft in the air, these generators generate electricity aloft that is then transported via cable. And similarly, the non-crosswind ones, usually the buoyant designs here, consisting of a balloon and a lighter that is filled with a lighter than air gas and a wind turbine inside. In my research, I mostly focus on the crosswind design, the fixed wing ground station, because our research has shown that they have the highest energy potential, especially when it comes to scalability. Because scaling up, for example, these non-crosswind motions, because they don't make use of this higher relative wind speed that comes with the motion itself, is rather limited. And as you've seen earlier, some companies use kites, others use fixed wings aircraft. So all of these bluely highlighted designs and concepts use different aircrafts. That might be different sorts of kites, or a fixed wing aircraft, or something in between, which you can see here on the bottom left, which is a semi-rigid kite with basically plates connected on hinges. All have different benefits and different challenges. For example, the kites usually move slower through the air, are therefore easier to control, are fairly safe, meaning if something goes wrong, we have a soft kite rather than a fixed fixed aircraft flying through the air uncontrollably. But at the same time, since they move slower, their energy potential is slower. And for the fixed wing aircraft, which is what most companies are using right now, as I've said, they move faster through the air, therefore can produce more energy, but are harder to control as they are so fast. And yeah, moving on to some potential markets. So this technology is still fairly new and, as you can see, quite unconverged. They aim at very specific smaller niche markets at the moment, most of them being off-grid communities that currently rely on expensive and dirty diesel generators. And also they might be in a location where PV, solar, or conventional wind turbines are just not feasible, like economically not feasible. So off-grid communities, especially here in Canada, often have the incentive to move away from fossil fuels. And yeah, and other potential markets that these companies are looking at the moment are mines, often also in remote locations, and not with the energy demand of a large city. So this could also offset some of their CO2 emissions. Another potential market, this is something a German company discovered, or rediscovered. I mean, we've been using wind energy for propelling boats and ships for centuries so far. They are using a kite to pull large tankers or ships through the seas, thereby offsetting or reducing their fuel consumption, and also thereby reducing their CO2 emissions. From what I've heard is that since fossil fuels are fairly cheap at the moment, and these ship tankers usually run on the most cheapest and worst fuels that are out there, these kite systems are economically feasible only in a few regions where the winds are also beneficial, going in their favor. However, they exist and they're doing fairly well from what I've heard. And another potential market, and this is a company from the Netherlands, it's called Ampex Powers. They are investigating the repowering of old offshore wind turbines. And what that means is as soon as a conventional wind turbine reaches its maximum lifespan, they strap off the tower, they take off the turbine blades, and what is left is basically this monopile. And instead of leaving it out there just like this, or pulling it back in, or repowering it with a new conventional wind turbine, they want to use this to set up one of their takeoff and landing platforms and use it to generate high-altitude airborne wind energy systems, which is especially interesting as we scale up, because for one, we're offshore, that even if something goes wrong, it's fairly safe. But it's also quite interesting because the wind conditions offshore are usually beneficial for wind energies in general. Now, as we scale up, airborne wind energy does not only have to compete with conventional wind turbines, but also with renewable energy sources and CO2 neutral sources. And what you can see here is the cost development over the last decades for PV solar and conventional wind turbines in gray and in yellow. And as you can see, the cost dropped tremendously, which is great. This way we can have more renewable energy sources within our grid, but at the same time, for a new energy source to be able to compete in this market, we need to be able to produce energy at very low cost. And one of these companies is aiming at this little blue line here. So they want to have a market entry in the next 2 to 5 years. This data is actually coming from Kite Power Systems. They are a manufacturer from Britain that got a lot of money from E.ON a couple of months ago. So quite interesting. That is their projection, and they see that airborne wind energy has the potential to be the next leap in wind energy production. Now, I've talked about the benefits and the markets, but I also have to mention the challenges, because this new technology still has a lot of challenges that it's facing. And I know this looks really complicated, and it's supposed to be complicated. It's just here to visualize what an autopilot could look like. Because if you want to reduce the cost, if you want to show continuous production, we need to be able to remove the human as a control unit or steering unit out of this loop, basically. So we need to be able to have continuous, autonomous production, and not only for a day, but also for weeks and weeks and weeks, and month and month and month, and ideally years without any human intervention. So what that means is that our autopilots need to be very sophisticated. And there's a lot of progress being made in this field, but these autopilots need to be able to deal with changing wind conditions, changing weather conditions, and they need to be able to do this reliably for years without human intervention, basically. Now, another thing that I wanted to show here is takeoff and landing is another big problem. As I've said, these devices need to be able to land and to take off in various wind conditions. So usually you want to take the device down when the wind is too slow, but you also want to take it down if the wind is too strong. So an autopilot needs to be able to land safely, even if there are gusts and strong turbulence in the wind, without crashing, so that the device can take off afterwards again. And with this very confusing picture, I wanted to show the the current situation in the regulatory situation, in the situation for these companies, because different companies aim at getting the device regulated under different names, basically. So some companies say, hey, it's a tether to the ground, so therefore it's a structure, while other companies says, well, it takes off like a drone, it looks like a drone, why not certify it as a drone? While others say, like, well, it's basically an aircraft, so it should be regulated like an aircraft. And all these regulatory bodies have way different demands to safety, to reliability, and all these other things. So there are a lot of regulatory things, regulatory hurdles, and a lot of these companies have different approaches, which also makes it a little bit more difficult to enter the market. Another thing often is overlooked is that wind is not only clean in a way that it doesn't produce CO2, but it's often noisy if you're fairly close to a wind turbine. I know if you've ever been close to a wind turbine, you stand underneath when you can hear the sound of the wind turbine itself. And nobody ever investigated this for airborne wind energy devices. Technically, as they're going high up in altitude, the sound should be less. However, you have a tether that moves through the air at the same time. So there will be some noise coming from these devices. And it needs to be investigated, as well as the shadow of these airborne wind energy systems, basically the human acceptance of these devices. And as an engineer, if something can go wrong, it will go wrong at some point. It's the purpose of an engineer to reduce that risk and reduce the impact. So if we can get these devices flying for years and years on end, what happens if at some point the tether snaps? What happens if the material corrodes, or what happens, for example, how large does the safety radius need to be such that no human is harmed and everything is still safe? These are still questions that need to be investigated. In the last couple of decades, as conventional wind turbines got taller and taller and taller, they faced more and more harsh weather conditions. And as you can see here, lightning might make for really cool pictures, but at the same time, they're not that good for wind turbines, which is why they usually have lightning protection. But at the same time, airborne wind energy needs to be able to deal with these weather situations as well, probably even more so as they are higher up in altitudes. And another thing, of course, is corrosion or heavy weather effects. For example, how does a kite or an aircraft deal with hail, snow, and rain? And all these weather situations take a toll on conventional wind turbines. They erode the system, they make the structure weaker, which means we need to maintain them at a certain interval, and this is also something that needs to be investigated and contributes to the overall cost of airborne wind energy systems as well. Now, moving on to my research, and I hope this time I'm a little bit faster. There we go. So I'm going to keep this short because I wanted to give a broad overview of the airborne wind energy systems in general. This is supposed to show certain wind situations measured in Pritzwalk, which is in northern Germany or northeastern Germany over a flat land, so great onshore location for wind. And in fact, close to this measurement location, about 2 kilometers away, there was a wind farm. And yeah, so in red you can see these measurements, and in blue you can see a simulation of the wind so changing in wind speed on the x-axis, on the y-axis you can see the altitude. So what that goes to show is that wind is not smooth and not always easy to predict. The wind does not steadily increase with altitude. It changes every time, every minute, every second, and it's different in every location. So as conventional wind turbines have standard models for lower altitudes, we need to develop, and I'm working on this, to develop a more reliable information for higher altitudes as well. So basically the main takeaway here being wind changes and it's not always smooth, which adds a lot of variability in the wind energy itself. And as we move on, we want to sell these systems. We want to sell our energy to the customer. We need to be able to provide something that looks like this. This is a power curve. So here you can see power over wind speed for a conventional wind turbine. Basically meaning we do our resource assessment at a certain location. We have a certain wind distribution, we can say with a certain reliability, a certain percentage of chance, we have at least X amount of wind, therefore we can sell Y amount of energy. This is for a conventional wind turbine. However, for an airborne wind energy system, there is no concrete power curve yet, as there are so many different designs and so many different paths they could take that this just doesn't exist yet. So currently what happens, and what a lot of people are researching, are how these power curves could look like, or how the optimal power curve could look like. Because these devices are flexible, they can move around and don't always have to go in a certain trajectory and don't have to move in circles, unlike a conventional wind turbine. So what you can see here is a path optimizer. So each of these little planes, or these little yellow bars here, is symbolizing the airplane or the tethered aircraft at a certain point in time. And what we do is we give it a certain initialization. We initialize it with a starting path, here a circle. And then we let the optimizer do a thing, and we optimize, for example, for maximum power production. And what it ends up being is that it looks something like this. So it optimizes, and it ends up with a different trajectory. That could look something like this, but for a different device, it might look totally different. And for a different wind situation, the path might also be totally different. So here you can see when the optimizer does its thing, we initialize it with one initial idea, and it will find a local minima. After tons and tons of iterations, it'll end up maybe with this path for a given wind situation. And as you can see here on the right, in green, this is power production of the pumping design in this case. Green is power production, and red is power consumption. And after tons and tons of iterations, about 500 iterations, it ends up and says for this initialization point, for this wind condition, our power curve could look like this. But that might look completely different for another design, and might look completely different for another wind situation. And yeah, so this is also something I'm investigating, like finding out optimal altitudes, optimal sizes of these devices, optimal paths as well. Yeah, and that already brings me to the summary. Main takeaways: airborne wind energy can be the next leap forward in wind energy production. It is cheaper, as it has lower costs as it doesn't need a tower and doesn't need expensive wind turbine blades as well. And wind is changing. Wind is definitely different every time in every location. And many designs exist, and many designs want to get into the market, and they compete in these fields. So currently, I cannot tell you which design is going to be the winning one, or maybe there are multiple ones, maybe there are certain ones that work better in certain situations. But this is still something that a lot of companies are competing in. So yeah, and advantages, there is a high energy potential, and the wind on average is higher aloft. And due to the low capital costs, this can be hopefully the next step in wind energy production. Some challenges, and I think hope I made this point previously, is that we need to show continuous production, continuous autonomous operation of these devices to be able to sell these devices to our customers. And therefore, we also need to demonstrate how safe our products are, or these airborne wind energy systems are in general, and that they're fail-safe. In case something goes wrong, they will still be able to land safely and not harm anybody. Yeah, so these are some of the challenges. Grid compliance, depending on scalability of these devices as well. As I said, currently they're mostly aiming at off-grid communities that don't have to have this compliance necessarily, or have different needs and demands. And before I leave you, this is a quick summary of some institutes and research institutes and companies that are working on airborne wind energy worldwide. And University of Victoria, this is us here. So we're also part of this community, and we're working on hopefully bringing airborne wind energy systems to the market fairly soon. And yeah, I want to say thank you to Stephanie and everybody to organize this great event here. PIX for sponsoring my PhD here at the university, as well as the Fraunhofer Institute in Germany, who helped me with my measurements, and the University of Oldenburg in northern Germany, who helped me with my simulations as well. And yeah, so thank you very much for your attention, and I will be gladly take any questions that you might have. Thank you very much.
Great, thank you for that. That was terrific. Do we have some questions? I'm going to move this microphone around, and please speak into it so our people online can hear.
Thanks, Marcus. You might not have this information to hand, but it would be helpful if you could tell me some world records. I'd like to know the world record power production and the world record duration for continuous power production.
For airborne wind energy systems.
Airborne wind energy. Or, you know,
most of these,
I want to know sort of what's been achieved in the field in terms of power and duration.
Yeah, so when it comes to power, most of the current designs that are out there operate in the kilowatt scale. So they have like prototypes that are in the order of 100 kilowatts, for example. The Makani design, and I think I can show you a quick video in the background if you're interested. I hope that's going to do. Yeah, okay, so this is the Makani design. This is their latest prototype. It's called the M6. I think it has like 600 kilowatts at which it's flying right now. That was their first flight in 2016. And it operated at an altitude of about 300, 400 meters, if I'm not mistaken. Maybe a little below. But they're still working on this. And other companies have slightly smaller scales for prototypes. For example, the small one that I've showed you earlier from TwingTech had a few kilowatts in power. However, they were able to show at least 24 hours of continuous operation. I'm not really sure. So I was at the Airborne Wind Energy Conference end of last year, middle of last year. And what they said is that they could have flying longer, but there was hardly any benefit to be gained at that point for them. They were kind of trying out the new controller and figuring it out. And after it was in the air for 24 hours or 32 hours, they said, like, okay, it works. So now we have to move on to the next step. So I think what they need to do is hopefully find somebody who sponsors a longer flight and then demonstrate that it works for months and enter the market that way, I hope. So I hope this answered your question.
Very much. Thank you.
Thank you.
Other questions? Please introduce yourself if you would.
Certainly. I'm Rafe Sunshine from the BC Sustainable Energy Association. And my question is regarding air safety.
Yep.
Small planes, drones, that type of thing. When you have this airborne wind system, what do you see as the solution for such a challenge?
When it comes to air safety in general?
Yes.
So different companies and I think there are different approaches that you could take. Ideally, you want to have a fail-safe autopilot that can safely land in case something goes wrong. In case, for example, the tether snaps, it should be able to land safely, or at least land somewhere where it doesn't do any harm. And therefore, I see, for example, the fly generators, as Makani has, may be beneficial at that point because they have these onboard propellers that can still control the aircraft in case something goes wrong. I think this might be the best thing they could aim for, like hopefully safely land, hopefully without crashing the airplane as well. But other than that, for now, I think it's important to have a certain safety radius around these devices, whether that is 1 kilometer radius or 2 kilometer radius.
So would that be part of the government regulations for regulating such a system?
Yeah, I think that's definitely needs to be regulated at some point. But as I said, like most of these companies are not even sure on how they want to be regulated, and whether it's the FAA or structural regulations at that point is really hard to find. So it needs to be regulated, but at the moment they're still in the phase where they have prototypes they want to show for a few hours rather than continuous operation. But as soon as they want to go into continuous operation, they will need to show that safety radius and safety features.
You mentioned also about the north. Canada has a lot of northland.
Yeah.
And as you say, it has a lot of wind potential. So I was wondering regarding this system, whether it would work for not only small communities, but actually be able to produce energy that could be exported along to other communities.
Right. Potentially as it scales up. As it is now, the scale of these devices is too small. If we assume that it's scalable, potentially yes, but at that point it also you have way more other players interacting as well. So you need, for example, the grid connection at that point needs to be able to be strong enough to be able to transport that much electricity from far away distances. I would say energy potential, yes, but there's so many other factors that play a role here. It's hard to say.
Thank you. Appreciate it.
Thank you.
Great. Other questions here? I think we'll go here and then I'll come over here.
Thanks. It's Adam Monahan from Earth and Ocean Sciences at U of Vic. So in the flight path of one of these airborne wind energy systems, they move through a fairly large range of altitudes and could be experiencing a fairly large range of environmental conditions other than just variations in the wind.
Yeah.
So are these devices equipped with, for example, thermometers to measure the air temperature they're moving through, to determine if they might be moving through an air column where they might have the propensity for the turbines to ice? The propellers to ice?
De-icing was actually mentioned at the conference too. I know that they're equipped with tons and tons of equipment, tons and tons of measurement devices at the moment, probably because they are prototypes, probably because they want to get as much information as possible. Whether that is necessary in a large-scale deployment, I don't know. It could also be that you want to have, let's say you had a wind farm of multiple of these airborne wind energy devices, you might have LiDAR measurement devices that measure where the wind is coming from, might be able to measure certain situations before they occur, thereby able to change the control schemes for these devices before, for example, a gust hits. When it comes to temperature sensors, I'm not sure if they do. I assume they do, because I talked to a few of these companies at the conference, and they want to get as much information as possible on these devices. So I think they do have that, but de-icing and ice weather situations are definitely not to be underestimated, I believe, yeah.
Ralph Evans, Civil Engineering at UVic. A couple of quick questions just about the potential of these systems from a very basic level. So on the resource side, you showed the boundary layers. What's the total wind power you can get at this typical altitude versus a more typical hub height?
Well, it depends which kind of device you're looking at. If you look at like a stationary one, then the power curve would look something like, let's say you had a conventional wind turbine, but just built extremely tall, right? The power increases with the velocity cube. So if you have a doubling in the velocity, you have a quadrupling in the no, eight times. You have 8 times more the power, sorry. So with an average wind speed increase in these higher altitudes, you will get way more power out of it. Of course, at the same time, density variations and density drops, but on average, you get way more power out of it as you go up higher. That is with the conventional stationary one. If you have these moving airborne wind energy systems, because of the relative velocity increase, because of the motion of the device itself, you could even increase the energy potential even more.
Okay, so you'd be hoping for maybe a doubling in average wind speed would be plausible by the height increase?
Wind changes all the time.
Yeah. But some average you might get higher.
Hard to generalize that at the moment. What we found out in our measurements is that there are different altitudes at which the wind is on average strongest. For example, let's say in the lower 500 meters, whatever. Might even be most economically feasible for these devices not go any higher at that point, because as you go up, as you scale up, the tether gets heavier, which drags the whole thing down. You have more losses. So let's say we stay within the lowest 500 meters, which is still a wind speed increase of, let's say, 20–30%, let's assume. That would still increase the overall power output significantly.
Okay. And you sort of answered my second question, but looking at the typical power curve you showed with the cut-in speed and so on, those are the standard problems of designs, that they don't work well in low wind, they don't work well in high wind, it doesn't really ramp. Are there benefits to this kind of device that they can get around some of those issues?
Well, there will still be a cut-in speed. This thing might not be able to take off when the wind speed is below 3 meters per second. However, if you look at the design that Makani is building, they have these drone takeoff. So even if there's a calm below, they might be able to reach altitudes where the wind is strong enough to keep this device afloat, so aloft. So there is definitely the potential that this kind of device, because it's flexible, because it can move around as it will, to kind of aim for altitudes where the wind is strong enough. However, if there's a calm all the way up to 500, 800 meters, it will have to land at some point. But you could technically aim for altitudes where the wind is strong enough. So let's say you take off, you find that you have highest wind speed at 200 meters, you can produce enough energy, but then there's a calm at 200 meters, but then you go even up higher and can continue production of energy. So there's the potential, but you need to be able to measure this at a given time, and you need to be able to control the device so that it safely reaches these altitudes.
Thank you.
Thank you.
Helen Bailey, ISVIC. Thanks for that presentation, Marcus. It was great. I was wondering, your devices, a lot of them have a tether with the electricity cable down. Is it possible to remove the tether and have electricity generation on board with some form of storage, or is the weight of that storage too great? I mean, to have the device effectively without the tether?
I would assume that the weight actually would drag it down too much at that point. That is my initial guess. Even though I have to admit I didn't investigate that further, that design. I'd say technically possible, but definitely quite heavy. What we found is, for example, as I said, like as you scale up, you make these devices bigger, they can produce more energy, but at the same time you need significant tethers because the forces are getting quite strong. And these heavy tethers, not only are they heavy, but they also have a lot of drag. So at that point, it pulls the whole system down again, and you don't get all these benefits. So these are like counteracting things happening at the moment. Thank you. Basically, you want to go big, you want to go high, but at the same time, this is kind of counterproductive. So it's really difficult to balance this. And my gut feeling would be, I think that's probably too heavy to keep it aloft.
Okay, thank you.
Other questions? So I have a couple questions. One is any possibility of making the whatever the form is of the device to cover it with very, very thin, lightweight solar panels to boost the energy by even 10% or so. Any thoughts on that?
There was actually somebody who did an energy calculation on that who said basically what his takeaway was that you could increase the overall energy production, but the weight of these things as it is right now would be very, even if it would add a little bit of weight, would drag the whole system down a bit. And comparing the surface area of these devices and the energy that can be harvested from that, and comparing that to the energy potential that is in the wind, it's just orders of magnitude difference because we have these, the correlation, or not the correlation, but the energy is relative to the cube of the velocity. So the overall electricity that can be produced from the wind is such, it's just orders of magnitude bigger than the one that could be harvested by PV solar at the moment. So therefore, probably not being done.
One could imagine, I'm just now thinking further, one could imagine, though, that you could have a farm of these airborne devices with solar on the ground.
Yeah,
maybe.
definitely.
Yeah,
That would
so
be
combine things
yeah.
to try and maximize.
I think this is a good idea because this would be within the safety zone where nobody is supposed to enter anyway.
Yeah.
So yeah, definitely.
The other thing is when you were showing your modeling of the wind profiles, two questions came up, but one was, how much variation is there from, this end of a field to that end of a field, and does the movement of the device in any way follow the energy of the wind? I'm trying to say there, can it seek out?
Can it seek out these like high energy pockets or the high wind speed pockets?
Yeah, because as you say, you've got gusts, it's continually changing.
Yeah, it's quite interesting. Moritz Diehl from the university, I forgot where he was from, in Germany, he had this idea where he wanted to position LiDAR devices around these airborne wind energy systems, and then he wants to aim for these high wind speeds to produce more energy, which, could be done, but at the same point, the question is, do you really want to have this spike in electricity production? Because ideally, you want to have continuous production for a longer time, and a spike in the energy grid is not necessarily what you want to have. Maybe the grid is not able to handle, so you might need some buffering at that point to be able to offset these energy spikes, to smoothen out the grid input a little. However, there are other effects at play as well. For example, if you have multiple wind turbines behind each other, you have a wake effect, basically a reduction in wind speed behind these wind turbines. And for airborne wind energy systems, because they're more flexible, let's say the wind footprint, the reduction in wind speed is less significant as what we see right now in our simulations, but it definitely still exists. So there is some energy loss if you have like a farm where these devices are too close to each other, for example.
Great. Yes.
We have farmland out on the Saanich Peninsula. They have problems with geese that come and eat their crops. Now, I'm wondering...
You want to slice them up with a tether?
Well, I'm just thinking that it would be very fortuitous as the farm would be a certain area that would be have the potential for wind energy, and it could offset some of the cost that the farmer might have.
Exactly, yeah.
And then it could also be a deterrent to the geese coming on to his crops.
Yeah, definitely. Yeah, there's definitely this potential. We basically need to find, or these companies would need to find somebody to buy this electricity, right? It's not only that we want to set up a prototype that just sit there. No, we want to produce electricity. So There's definitely a chance to set these devices up, I believe. And why not on farmland? I think that's probably a good area if their safety zone is big enough.
Thank you.
Did you have another question?
So, you know, we're so addicted to electricity, I wonder if we perhaps miss the point. It's about energy. And in the Airborne generator, it's generating electricity and then transmitting it. But the other, it's not. It's generating mechanical motion, right? It's pulling.
Yep.
So it's pumping. So are there other investigations where we might look at integrating the services provided by this as mechanical energy services and not electrical? So grid connectivity is not all and everything, particularly in other parts of the world.
Definitely. So what I've seen was that they, in third world countries or emerging countries, there was the idea of basically building like a small, taking a small kite, that because often these smaller communities don't necessarily need like a big surf kite or whatever, but taking a smaller kite to actually pump water at that point, and because the motion, as you said, is already a pumping motion, so it could be definitely used for that. And there were, I think, a few universities, or 1 or 2 universities, had like a group investigating this. I don't know the state of this project right now, but there was that idea too, and I think it's something worth investigating. And could also be used for, like if you have a small kite, you can basically have it on the backpack or something, and small generator on the back. Yeah, why not? No, definitely.
Okay, any more questions? No? Well, let's thank Marcus. Thank you very much.
Thank you. Thank you very much.